Hey everyone, this is a video lesson that I use as a supplement in my AP Calculus AB class that goes along with the second section of our limits unit, which is called Limits with Infinity. I'm posting this online for anyone to access just in case it would be helpful to others out there. You should know that I always have a printable set of notes that go with these lessons, and if you would like access to those notes, you can find a link in the description. If you are one of my students, you should definitely have these notes printed because I did it for you. And you should be writing stuff down as we go over the lesson. I encourage you to pause the video as much as you need to write things down or go back and listen to something again. And also, as always, I encourage you to ask me questions if there are parts that you don't understand after you view the lesson. All right, let's get started. We have a little warm-up here where I show you limits, and hopefully at this point you're getting comfortable with this limit notation. And for each of these, I want you to try to come up with the answer to the limit. And in the directions, it says think about what the given function would tend toward as n gets larger and larger to determine each limit. So that's sort of a little hint. There is another hint in the note toward the bottom. You never really substitute infinity. So the first thing you need to know for this new section is we talk about using substitution as a method for finding limits. Well, you don't write 1 divided by infinity. That doesn't really work very well. So what I want you to do instead is I want you to think about what happens when the limiting variable, in this case it's n, approaches infinity. Use numerical reasoning, and again, the directions tell you basically you need to think about what happens as n gets larger and larger. What happens to the value of the expression given inside of the limit. So I encourage you to pause the video right now and think about that for yourself. I am going to move on, and I'm going to show how I did it. Again, if you'd like to pause at this moment, go ahead. Okay, so here's what I did for number 1. I set up a little table of values where I just chose any starting point for my n value. So I decided to start with an n value of 1, and I'm using the expression 1 divided by n to see what comes out. So 1 divided by 1 is 1, and that's the first row in my table. I then make n larger, and I can choose any larger value than 1 that I want. So I just decided to go by tens, like multiples of 10 here. And so what I'm finding here now is 1 divided by 10, and I just wrote that as the decimal, 0.1. 1 divided by 100 is 0.001, and so on. And I hope what you see is that as n gets larger and larger and larger. And again, we don't have to pick these particular values. So if you paused and you used different values, you should probably be able to see the same thing fairly easily. What's happening with our 1 over n value is that it's getting smaller and smaller, and in particular, it's getting closer and closer to 0. So the answer to this limit is 0. And so this is just a good starting point. It's a good way to, let me change that. It's a good way to start to think about infinite limits when your limiting variable is tending toward infinity. You can think of that as making it unboundedly large. For number 2, I did the same setup. I decided to start with an n value of 1. Again, you don't have to start there. That's just where I went. And I made n larger and larger and larger. And this time I'm using the expression n divided by n plus 1. So my number divided by 1 more than my number. And so 1 divided by 2 is 0.5. 10 divided by 11 is 0.909, and so on. And as you can see, making the n value larger and larger and larger, n over n plus 1, that expression is getting closer and closer to 1 this time. And so this is just a little warm-up to start to think about seeing infinity in a limit and how you can approach it. Before we move on, I would like to say that for the most part, this intro to seeing limits with infinity, it will be pretty heavy in approximation techniques, and we will be relying on the calculator throughout this section. I want you to know that as we move on through the course, we do revisit limits like this again, and we talk about them in other ways. but we wait on more exact methods until we know a little bit more calculus. So again, right now we're just sort of trying to get a feel for what infinity looks like within a limit, what we can do with it, the concept of infinity, and we will be talking about limits with infinity and how they relate to asymptotes and end behavior. Alright, so I have some very informal definitions of infinity and negative infinity that you can write down in your notes. If you see positive infinity, which we already saw, you can think of that as unbounded positive values, meaning you start somewhere for your variable and you just make it go bigger and bigger and bigger, or you will see that eventually what you get out maybe is going bigger and bigger and bigger, and that would be called positive infinity. If you were looking at it graphically, like I just put a random graph here, moving toward infinity along the x would just be moving further and further to the right on the x-axis or on the graph. And also, if you see a graph going up, shooting up like this, that would be called going to infinity on the y. Okay, negative infinity is the opposite. So if you are approaching negative infinity, you're starting with a negative value and you're making it more and more negative. So things like -1, -10, -100, -1,000, and so on, that could be used as a model for approaching negative infinity. Also, negative infinity is moving to the left along the x-axis, or if you see the graph going down, you would call that moving toward negative infinity on the y-axis. All right, before we do any other examples in the notes, I would like to just take a break from the notes for a moment, and I want to show you this resource because I just came upon it the other day and I think it's so cool. And I want to discuss it briefly. We're not going to actually do this. This is an exploration that I found from another teacher online. I'm not going to actually go over the entire exploration, but I am going to show you how it's used to show an infinite limit in a real scenario. So this is an exploration centered around the 100-meter men's freestyle, and its record in 1956 was 55.4 seconds. And then what you see as you go through the exploration are the different records and when they were broken or when they were hit. Okay, so in 1956, the record was 55.4. In 1957, the record was 55.2. Again in 1957, it was 54.6, and so on. Going back for a moment, just because I want to give credit to the teacher who posted this, I found this on a website called mathwithmrwood.com. And as you can see, it's a pretty fabulous website where he has a ton of different courses here, and I just happened upon this gold mine of AP Calculus stuff. And as I was looking through the limits and continuity section, I noticed that he has these investigations, and I thought they were really cool. So if you would like to go through the investigation for yourself, you can go to that site, again, mathwithmrwood.com. He has the investigation and he has solutions. I believe, yeah, it's right here, limits in athletics investigation and solutions. Sometimes he shows video solutions too, so he just has his act together. Look at that. One of these days, I would love to have a website that looks like that. Maybe. Hopefully. All right. So this is actually not all of the data. The data is a fairly large table. I'm going to click here and hopefully it'll take us to the activity just to show you how much data we have here. Yep, see? Okay, and it goes all the way until, what would that be, 2009. The record was at 46.91 seconds. And so what you can do with this exploration, what he has his students do with this exploration, is he has them take this data and put it into Desmos. And Desmos will create a scatter plot of the data. You'll see that it's a curve, and then you can also have Desmos create a regression model for the data. And what he is asking his students to investigate here is as the years increase. Okay, so remember, this is the years column. It's years after 1900. As these years increase, you can see that the time is decreasing, obviously because it's breaking a record for how long it takes to swim the 100-meter freestyle. And the question that he poses is it just going to keep going? Like, as the years go up, are we just going to keep going down, down, down? Meaning, like, as time approaches infinity, is the time for the freestyle going to go down to 0, going to go to negative infinity? Like, what? Is there a limit there? And what they find, okay, I'm just going to kind of skip to the results. He even has answer keys, and it's so nice. Like, look at that. All right, the results are, this is what the scatter plot looks like, and this is what Desmos comes up with as a regression model that is graphed there as well. You can see that in the curve. And how we can set up the question that was posed is as a limit. The limit as time approaches infinity, remember time was the x here. I don't know if I explicitly stated that before or not, but time is the x, and meaning years, and the time that it takes to actually swim the 100-meter freestyle is the y. Okay, so what we could do is the limit as the years approaches infinity of the regression model, what we're finding is we're getting a value of 44.419. And I don't expect you to completely understand where that number comes from. However, you may notice that it's right there. So we'll talk about that eventually. So that's showing us that, the answer to, is it just going to keep going down, 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 is no, it's not. There is a limit. Is this an exact answer? Is somebody actually going to hit this and this will be the lowest time ever? No. This is a model. It's not exact math, but it is saying that for sure it's not just going to keep going down forever and ever to 0. That doesn't make sense in the context of what we're talking about here. And so that's just a nice little intro to how you can look at a limit in a real life scenario. Something that you may notice before we move on, because this takes us back into the notes, the next definition that we need, is that whenever we're looking at these graphs, you're going to see this a whole lot, this graph and this graph. What you are seeing are asymptotes, okay, and that's on purpose. Limits involving infinity are used to describe or to define asymptotes. And so back into the notes now, here's a definition that you need. A horizontal asymptote. I would assume that prior to calculus you have heard of asymptotes, you've heard of horizontal and vertical asymptotes. However, they have probably been defined fairly loosely, and that is because to define a horizontal asymptote, as you see here, you use limits. Okay, so let's take a look at this definition. The line y equals b is a horizontal asymptote of the graph of a function if you can either say the limit as x approaches infinity of the function equals b, or the limit as x approaches negative infinity of the function equals b. Now, it's important to note that you don't have to have both of these limits. You don't have to have the limits equal to the same thing. Notice the word or in here. The little graphical example that I put here is actually an example where we have two horizontal asymptotes, as you can see. And so we would have two limits that give us two different answers here. And so the limit as x approaches infinity, if I just move, let me grab a color here. If I just move along this graph further and further to the right, that would be, modeling x going to infinity. I'm looking about in there. Okay, that is tending toward a y value of 1, and so we would say that that is equal to 1, and that means that there's a horizontal asymptote at y equals 1. As we move toward negative infinity, that would be moving further and further to the left in this direction. We see that our y is getting closer and closer to negative 1, and so that would be the answer to this limit. This one would be negative 1. So again, these do not have to be equal. Notice the word or there. It is important. So the first couple of examples, I'm just going to show you how you can set up identifying horizontal asymptotes of a function using the definition. And again, we're going to sort of use approximation techniques more so than anything else right now. because we just want to get an understanding of how to set these up and where infinity is involved. Okay, so for example 1, if I'm trying to find the horizontal asymptotes of any function, the first thing that I want to do is I want to set up two limits. I want to set up the limit as x approaches infinity of my function. I'm just going to write f of x, knowing that f of x is this, 2 plus 1 over x. And the other limit I'm going to set up is the limit as x approaches negative infinity of my function. And so what you would want to be thinking about now is what happens when I plug something in for x, and then I plug something larger in for x, and then I plug something larger and larger and larger in. And so, some of you may be able to see the answer right off the bat. Some of you might want to think about it a little bit more. Maybe you even just want to go to your calculator here and do some numerical analysis like this. 2 plus a tenth, 1/10. So I'm starting with an x of 10 this time. What's that? That's 2.1. Okay, now let's make x larger. So instead of doing 2 plus 1 over 10, let's do 2 plus 1 over 100. What do we get? 2.01. And you can keep doing that process if you would like to. I usually suggest to my students that they do 3, just to feel good about it. For right now, because we are using our graphing calculator, you could also go to the graph of the function and see what's going on there. You could do the table as well. Oh, my window is all messed up. Let me fix that. Here we go. And we could see that as we are moving further and further to the right, that would be doing x to infinity. Our y is close to 2. Okay, so that's the answer to the first limit. Just because we already have this graph here, moving in the other direction would be modeling x going to negative infinity. And what I want you to notice is this is an example where you are ending up with the same answer. Take a look at your y coordinates as I move further and further to the left. Notice it's 1.9. If I would want to, just be super sure about that, I could say let's do 2 plus 1 over negative 10. 2 plus 1 over negative 100. And so on, and we can see that we're still tending toward 2. Again, they won't always match. They don't have to match, but in this case they do, and that just means that we're going to conclude that there is a horizontal asymptote. I'll just abbreviate with HA, and that horizontal asymptote is at y equals 2. So the result of your limit here, or the results of your limits, if you have more than one answer, that's where your horizontal asymptotes are. Okay, so usually if I was doing this set of notes in person, I would tell my students to try example 2 on their own now that they sort of understand how they need to set it up. So if you would like to pause and try this one on your own, go for it. I'm going to go ahead and set it up here. Again, I'm just finding the horizontal asymptotes. Okay. And so I know that if I need to find horizontal asymptotes, that means I'm taking a look at the limit as x approaches infinity of my function, and the limit as x approaches negative infinity of my function. Okay. How I'm going to approach this one is I'm going to take the function and put it into my y equals editor. And I'm going to show you how you can set up your table to see this one. We could look at the graph and it's going to give us the answer fairly easily. Go back to a standard viewing window. But sometimes students are wary of reading answers from a graph like this. So I'm going to show you how to change your table settings in case you don't know this. Ooh, I already have them kind of crazy here. You probably don't have these same values. Usually your table start is 0, and this little symbol is delta, a delta symbol, which means the change in. So it's like how much are you going to change the x for each row, and it's usually going by 1. So the table usually looks like this, right? But this time, because we want to look at x going to infinity, I'm going to go back to that table setup, which I got to that by hitting second and then the window button. And I'm going to say let's start with a table value, or an x coordinate of 10 maybe, and let's go up by 50s. I don't know, I'm just picking numbers. I'm saying here's my starting point, and then I'm going to make it bigger and bigger to see what's going on. And so that's pretty nice. So as my x goes bigger and bigger and bigger, notice that my y is getting closer and closer to what? 1. Going back, I always get so confused. Where am I? All right. We're going to do the same now for x going to negative infinity, and sometimes it's difficult for students to think about where do I start and where do I go. Okay, you can start wherever you want. So I don't know, start at negative 10, start at negative 100, it's up to you. Go by whatever you want here, and then scroll through your table. Okay, so I want to scroll up this time through my table, and notice that it's just nicely shown as negative 1. And so this is an example where we get 2 different answers to our limits, and these are not one-sided limits. It's not that thing that we talked about in the first section where these have to match for the limit to exist. This is just saying that there are 2 horizontal asymptotes. There's a horizontal asymptote at y equals 1 and at y equals negative 1. And that's by the definition, the limit definition of horizontal asymptotes. Just going back to that graph one more time, you could probably pick that up from the graph. You can see as you move further and further to the right, your y coordinate is getting closer and closer to 1. And when you move further and further to the left, the y coordinate is getting closer and closer to negative 1. Alright, so that's a couple of examples of how you use an infinite limit to show a horizontal asymptote or horizontal asymptotes if it has more than 1. In example 3, we just have a limit here. We're going to find the limit as x approaches infinity of sine x over x. And this is one where I like to review how you can use sandwich theorem to find a limit. In my sandwich theorem lesson, I said that sometimes sandwich theorem lends itself very nicely to some infinite limits, so I go over a brief example of that here. Now this limit might look familiar because we've already done a limit with sine x over x, and we kind of proved it using the sandwich theorem back in that video. But I want you to keep in mind that that limit that we were talking about earlier in this unit was the limit as x approaches 0 of sine x over x, and we found that to equal 1. This is not the same limit. This is the limit, as you can see, as x approaches infinity of sine x over x. Now, I'm not saying that you necessarily need to use the sandwich theorem to find this answer. You could probably just reason through it. You could use a calculator approximation method, as we did for the other two. But I just find that this is a good time to go over the sandwich theorem again, so let's just go for it. Okay, so what I'm going to do here, because I have a sign in the numerator of my function, I know that I can take that out and sandwich it between negative 1 and 1. I'm like all flustered right now because the thickness of my pen keeps changing. I'm just going to roll with it. It's fine. It is what it is. Okay, again, that's just the range of sine. Think about the sine wave. It just goes back and forth between a low point of negative 1 and a high point of 1, and so that's why we can set up that compound inequality. Now, we also need our sine of x to be divided by x. So let's put that right here. Let's put that here. And let's put that here. Now, we're allowed to do that as long as the value of x doesn't change the sign, SIGN, like positive, negative, of each piece of the compound inequality. And that's not going to happen here because notice the x is going toward positive infinity. So we're not talking about negative x values. And that's why we're allowed to divide everything by x and not have to worry about, well, does this flip? It doesn't. Okay, so once we have the middle of our compound inequality matching the function that's in our limit, we can apply the limit that we are trying to find to the ends of the compound inequality. So I'm going to write the limit as x approaches infinity of negative 1 over x. That's this piece over here. I'm going to find that answer. And I'm also going to find the limit as x approaches infinity of 1 over x. Hopefully they have the same answer because that's part of sandwich theorem, that these limits match, and if they match then the middle limit has the same value. So we already did this one, the limit as x approaches infinity of 1 over x. It was just in n form. It was number 1 in the warm-up. Remember we said let's let n equal 1, 10, 100, and what we saw was that our 1 over n, or in this case it's just 1 over x, is going to 0. Now what I want you to think about is this answer also going to be 0? So think about negative 1 over 1, that's negative 1. Negative 1 divided by something bigger like 10, okay, that's negative 0.1. Negative 1 divided by 100, that's negative 0.01. It's negative, but it's still getting closer and closer to 0, just on the other side of y equals 0. And so our limit answer is still 0 here. It's just, a negative decimal value close to 0. And since these do match, we can say, therefore, the limit that we're looking for, which is the limit as x approaches infinity of sine x over x, is also equal to 0 by the sandwich theorem. I'm just going to abbreviate that. Okay. Finally, before we move on to talk about other types of limits, here's one more limit where x is going to infinity, and this note is pretty important. Remember, whenever you're doing any sort of calculus, you want to make sure you understand the properties. So in section 2.1, we discuss properties of limits, and those properties allow us to do things like add, subtract, multiply, and even divide within a limit, so long as the denominator isn't 0. All of those properties still hold for limits with infinity. And basically what that means for us is that we can use manipulation techniques to move some parts around in this limit that looks fairly complicated, but I think you'll see that once we move some pieces around, it's going to be an easy answer. Before I do the manipulation techniques, though, I want to mention that we are going to use this answer. Okay, we proved it using the sandwich theorem, so we're happy with that. And so here's what we need to do to move things around to find that limit that we already found and to answer this limit. All right, we are going to set up our limit again. And the first thing that we're going to do is split this sum in the numerator into the sum of two fractions with a common denominator of x. Okay, that's just a little algebraic move. And just by doing that, you may see the answer to this already, or you may see where this is going. The next thing that I'm going to do is I am going to split the limit over both pieces of the sum. And again, it's those properties that let me do that. Now with this first limit, I am going to think about the fact that these x's cancel or divide out so long as x is not 0, and it's definitely not 0 here because take a look, we're going toward infinity for x, so definitely not 0, which means we can write this as the limit as x approaches infinity of 5. Finally, I know that the limit as x approaches infinity of 5, or the limit as x approaches anything of 5, is just 5. I know the limit as x approaches infinity of sine x over x is 0 because I just found that answer in example 3, and so therefore this limit is equal to 5 plus 0, or 5. Okay, so that was just a little exercise that shows you that you can still use those properties to manipulate pieces of a limit even when it goes to infinity. Okay, for the next section of this set of notes, we need to talk about the result of a limit being infinity. Okay, so let's just jump straight into example 5. What we're asked to find here is the limit as x approaches 0 from the right of 1 over x and the limit as x approaches 0 from the left of 1 over x. Now, it may be important to note, okay, sometimes I have students who think about this stuff ahead of time and they're like, wait a minute, I remember something about this. And so before we do too much with this, okay, I'd like to write a little note. If I ask you to find the limit as x approaches 0 of 1 over x, you may recall that the first thing that you should try, and I hope you would probably try, is substitution. Just take that value and sub it in. You get 1 over 0, and that's undefined, right? It's not indeterminate. So if you were paying close attention to when we discussed this sort of limit in the first section, we just called this does not exist and we moved on. We said no more to talk about here. However, I did say that eventually there will be more to talk about here. Okay, I'm not arguing that this limit doesn't exist. I'm not saying that now it does exist. It doesn't. However, what we can do with this limit is we can break it up into its one-sided limits. We can say, let's look at the limit as x approaches 0 from the right and the limit as x approaches 0 from the left and see what's really happening here, and it'll help us understand the function 1 over x a little bit better. And so for this one, again, I'm just going to let the calculator do a whole lot of the work today to save us some time. I'm looking at the function 1 over x, and again, I'm going to look at my table. Here's the graph. You may know what this graph looks like already. I'm going to look at my table, though, just to show you very clearly here what is going on for each one-sided limit. So let's say start at x equals 0 because we're approaching 0, and we'll go up by a small increment this time because we're trying to start somewhere and then get closer and closer to 0, or I can sort of just maneuver that, model that in the table. I'm going to make a delta table value of 0.01. Maybe that'll work. Let's see. I should have wrote down what I did. Yeah, that works okay. Maybe I should do 0.001. That might be a little bit better. Yeah, I think so. That looks good. Okay, so to model this right-handed limit, let's start somewhere to the right of x equals 0, like x equals 0.06. And what I want you to do is as we move up toward x equals 0, look at those y-coordinates. We have 166.67, and we have 200, 250, 333. What do you notice about those y-coordinates? They're getting bigger and bigger and bigger. Until you get x equals 0, which is obviously an error. But the question is, if your y-coordinates are just getting bigger and bigger and bigger, what do you write there? The answer is you write infinity. So what we're saying here is that this is undefined. However, if we approach this function just from the right, we could call that limit value infinity. Okay, if I change my window a little bit here, just because I think sometimes it looks better when we look at a smaller window when we're approaching 0. You can see that graphically. So you're, again, starting at any x coordinate, and remember what you're doing. You are moving, you're not moving to the right this time. You're not going to x equals infinity. You're going to x equals 0 from the right. So start anywhere to the right of x equals 0, go toward x equals 0, and notice that the graph shoots up. That means that it's going toward positive infinity. What's happening on the other side? Take a look at the other side. Start somewhere to the left of x equals 0, move toward x equals 0, and notice that the graph goes down. So what do you think you would call that? You would call it negative infinity. And so saying that this limit does not exist is not wrong for two reasons. First of all, the left-hand limit and the right-hand limit are not the same. So the limit definitely doesn't exist. The limit as x approaches 0 definitely doesn't exist. But also, you could claim that it doesn't exist because infinity is not a real number. So again, I didn't say anything wrong back in the first section when we talked about it like that, but now we're just giving a little bit more information with it. Now, finally, bringing that graph back up, I hope that you recognize that what is happening at x equals 0 is we have a vertical asymptote, okay? And that's pretty important. Whenever you get an answer of infinity or negative infinity, when you are approaching an x coordinate, then you say that that function has a vertical asymptote at that x coordinate. That is the definition of vertical asymptotes, the limit definition. So the line x equals a is a vertical asymptote of the graph of a function y equals f of x if either the limit as x approaches a from the right of f of x equals either positive or negative infinity, or you could say you're approaching the x coordinate from the left, and again you're getting positive or negative infinity. Okay, so I'm going to go over the next two examples fairly quickly because vertical asymptotes is an idea that we will discuss later on again. Right now, all I'm going to tell you is if you are asked to find vertical asymptotes, you are going to be setting up limits again. You're going to be getting answers to limits to show that you have vertical asymptotes. However, you're actually going to figure out the answer to the vertical asymptote ahead of time and then just set up your limits to show by definition that they are vertical asymptotes. And so here's what I mean by that. When we are doing horizontal asymptotes, we could set up the limit as x goes to infinity. That was a part of the definition of a horizontal asymptote. We put an infinity here. And then we used the function and we found what the answer was. However, here, going back to that definition, take a look at what you need to do. You need to approach some value. The question is, what value? You know, you can't put an a here. You need to actually put a value. And so that's what I mean by you're actually going to figure out what the answer to the vertical asymptote is ahead of time. You're going to put a value here that you think is the vertical asymptote, and then you're going to show that when you take the limit as x approaches that value of your function, you get either infinity or negative infinity. So your answer needs to be infinity or negative infinity for it to indeed be a vertical asymptote. Okay. Easy thing for right now is that your vertical asymptote is going to come from whatever makes your denominator 0. I will have more to say about that in the next section when we start to talk about all different types of discontinuities, but for these examples we can just go with, you know, what's the restriction on x? You would all say x cannot equal 0, right? Because that would have a 0 in the denominator, which would be undefined. And so that is the value that we are going to approach. We're going to approach x equals 0. For this one, I'm just going to show this graphically because that's the quickest way to do it. So 1 over x squared is my function. For this one, we actually don't have to set up one-sided limits because if you take a look at approaching x equals 0 from the right and approaching x equals 0 from the left, you'll see that the graph does the same thing on both sides, and that is it goes up excuse me, to positive infinity. And so I can just do a very simple limit statement here. The limit as x approaches 0 of f of x is equal to infinity from both sides, so I don't have to put a plus and a minus here. And so therefore, I know for sure by definition that there's a vertical asymptote at x equals 0. For example 7, we are going to have to set up more limits here because it's not going to be as simple. Let's take a look at the graph first. So this time I have 1 divided by, make sure you group the denominator with parentheses, x squared minus 10x plus 16. I might need to change my window. Yeah, I do. I'm going to go back to a standard viewing window. Ugh, that one's not great either. But what I want you to see here just messing around with my window to get a nice graph. Yep, that's a little bit better. What I want you to see here is that there's actually 2 vertical asymptotes, and sometimes the calculator will like sort of draw them in as vertical lines. Okay, they're not really there as lines. You know, it's, if you were to sketch this graph, you would be sketching a curve that, you know, tends up toward that vertical line and down toward that vertical line on the other side, and then vice versa for the other vertical asymptote. All right, if we factor this function, factor the denominator, what's that, x minus 2, x minus 8, we could see that definitely our restrictions here are x cannot be 2 and x cannot be 8. And so that's where we're going to focus our limits for our vertical asymptotes. This vertical asymptote is definitely at x equals 2. This one is at x equals 8. We could see that from the table for sure. If I go back to a normal table setting here, start at 0, go by ones. Notice that there's an error for x equals 2. And there's an error for x equals 8. All right, I said we're going to have to set up more limits here, however, because the graph is doing something different on each side of these asymptotes. So what I'm going to do here is set up the limit as x approaches 2 from the left of g of x. I'm going to set up the limit as x approaches 2 from the right of g of x. I'm hoping those will be infinity or negative infinity. And then I do the same thing for the other restriction. The limit as x approaches 8 from the left of g of x, and the limit as x approaches 8 from the right of g of x. Again, I want my answers to be infinity or negative infinity to show by definition that they're vertical asymptotes. Going back to that graph one more time, and I'm going to fix my window again, just so we can kind of see it nicely. We don't need to see all of this. Let's do a, oh, keep that, an x-min of 0. There we go, that's pretty. For the first limit, the limit as x approaches 2 from the left, start somewhere to the left of x equals 2, move toward x equals 2, and what you see that is you're going toward infinity. On the other side, start somewhere to the right of x equals 2, move toward x equals 2, you'll see that it's going down to negative infinity. So we'll put an infinity here and a negative infinity here. It is the opposite on the other side for x equals 8. From the left, you're going to negative infinity. From the right, you're going to positive infinity. And so finally, we'll just put a little statement down here that says we have vertical asymptotes at x equals 2 and x equals 8. Yay! Okay, again, I said we'll talk about vertical asymptotes in the next section as well in more detail. So right now, I just need you to know that you need to look for your restrictions, set up limits, and your answers to those limits should be infinity to show by definition that you have vertical asymptotes at those x coordinates, x values. All right, finally, the last part of this section, we are going to end with, listen to this, we're going to end with end behavior. Isn't that perfect? Okay. Prior to taking calculus, I know that some students have heard of end behavior. You know, I don't know how much you remember if you have heard about end behavior though. So I'm going to show you a quick little example here of what end behavior looks like graphically, and then I'll show you the definition of end behavior. And then I'll show you a quick little trick to finding end behavior models for some types of functions. Okay, so if I'm looking at the function y equals 3x plus 2 over x plus 5, okay, here's what that function looks like in a standard viewing window. Keep in mind, standard viewing window is like x min of negative 10, x max of 10, y min of negative 10, y max of 10. Okay, so, you know, pretty close to the origin here. That's what our graph looks like. It's curvy, it has an asymptote at x equals negative 5, a vertical asymptote, it has a horizontal asymptote definitely somewhere as well. Okay, that's just a screenshot that I did of this function around the origin. Now, if I asked you to find an end behavior model for this function, what I'm asking you to find is a simpler function. Is there, like, you know, a simpler function that we could use instead of all of this craziness to model this type of function, or this function in particular, when you expand the viewing window of the function. And so what I mean by expanding it, you could think of it as zooming out, you could think of it as going out to the ends, that's why it's called end behavior, or you could think of it as approaching infinities. And so now what I'm going to show you is that function again. Okay, sorry, I paused it so that I could get it all set up to make the video a little bit quicker. Okay, so I'm showing you this function again, but what I want you to notice about my window is that I decided to expand it. I went out to negative 100 to 100 on the x and negative 100 to 100 on the y. This type of window doesn't always work, but I'm just trying to show something that says I'm looking out toward infinities on both axes to see what this function looks like. So again, this is what the function looks like near the origin, but when you zoom out, okay, when you go out toward the infinities, this is what the function looks like. So all of this curviness is happening right around here. And for the most part, what you see happening with this function is that it's just a horizontal line. And so we say that we could use the equation of a horizontal line as an end behavior model for this function. And it happens to be, if we go and change our table back to like 100, let's just go by hundreds. Okay, what I want you to see here is that your y, as we go out, is closer and closer to a y of 3. And so we would say here that y equals 3 is our end behavior model for this function. Okay, and again, an end behavior model is just sort of a simpler function that you can use whenever you are looking at very, very large x and y values for your function instead of values that are close to the origin. So here's a formal definition of end behavior models that uses a limit, you can see in the definition. So remember, an end behavior model is going to be used as a simpler function whenever you are just looking at very large, or I hate that, very small. Really what this means is, I don't like that, I'm crossing that out. Very large in the positive or negative direction values. I don't know where I got that definition from, but that doesn't jive with me. I just said the word jive. Okay. Anyway, so when we're moving out toward infinity or negative infinity, we can model the behavior of a complicated function with a simpler one. And we do that using this definition. So notice as this, it says the function g is an end behavior model for f if you can take f divided by g, take the limit as x approaches infinity, or notice here the limit as x approaches negative infinity, that's the left end, and you get 1. Okay, if you get 1 when you take this limit of this quotient, that's how you prove that you have an end behavior model. And so for this example 8, it says show that g of x equals 3x to the 4th is an end behavior model for this very long f of x function. So what I would encourage you to do right now is I would encourage you to pause the video, take this as your f of x, this as your g of x, and try to fit them into this definition to do what it's asking you to do, and that is to show that this simple function is the end behavior model. I'm going to pause as well, get it set up, and then I'll come back and show you what it looks like. Okay, I'm back, and as you can see, I have a lot of writing. You might need to pause the video one more time to write all of this down, but I'm going to talk through it, and so you can write as I talk as well. So I set up this initial limit from the definition. I'm looking at the limit as x approaches infinity of my f of x function divided by my g of x function. So this is my f of x, this is my g of x in the denominator. Now I'm trying to show that this limit is equal to 1. So now what I'm doing is a little bit of manipulation to, sort of maybe we could call it simplifying the function inside of the limit. So I split the differences and sums here into separate fractions, all with a common denominator of 3x to the fourth. And then I simplified further from there. 3x to the fourth divided by itself is 1. I canceled, common factors of x here, same here, same here, and same here. I also simplified things like 6 over 3, that's 2. Okay, now at this point I can finish my limit pretty easily, and I think at this point we should talk about something that's pretty important. Going all the way back for just a moment to this limit, yep, here it is. When your variable is going to infinity and you have a fraction where the variable is only in the denominator, I'm going to tell you right now that that is always going to be equal to 0. It doesn't have to be a 1 in the numerator. It doesn't have to be a power of 1 on the variable in the denominator. This answer of 0 would hold no matter what the value is in the numerator, as long as it's just a constant without a variable. So it could be 1,000 divided by n. If n's going to infinity, that expression is still going to 0. It could be, 10 divided by n cubed. If n is going to infinity, that expression would be going to 0. And so what I'm trying to say here is that this stays a 1. However, since there is an x in the denominator of this term, and x is going to infinity, this becomes 0. Since there's an x only in the denominator of this term, and x is going to infinity, this becomes 0. This becomes 0. This becomes 0. And so what you have as your answer to this limit is 1 minus 0 plus 0 minus 0 plus 0, or, that ends up being 1. And so that is proof by definition that 3x to the fourth is an end behavior model for the f of x function that you see there. Now, before we move on to the next example, I just want to ask you, do you see where this 3x to the fourth comes from? I think it's kind of clear here, right? It comes from sometimes I have students say, well, it's the first term, and I say, be careful. Let's call it the term of the highest power. Okay, the term of the highest power for a polynomial is always going to be the end behavior model. And that's a little shortcut that you can use, and you can even apply to something that looks crazy like this. Okay, now notice that this does not say show that you have a certain end behavior model from a function. Okay, it just says find the end behavior model. So these are much quicker examples where what you're going to do is you're just going to try to figure out for this very complicated function, what's a simpler function that models it as an end behavior model, and what you can use as a nice little shortcut every time. Okay, going back to the fact that here for this polynomial it was the term of the highest power. Well, for a rational set of polynomial functions here, you are just going to take the term of the highest power in the numerator over the term of the highest power in the denominator. And so we could say that g of x equal to 2x to the fifth over 3x squared. Simplify that to g of x equal to, what do we have there? 2x cubed over 3, or 2/3 x cubed. That is our end behavior model. And just to prove it, I am going to graph that. Ooh, so this is cool. Take a look at this. I graphed the original f of x function, and I don't even think I have to show more proof than a standard viewing window to you. Take a look at that. That is definitely looking like a cubic graph, right? Like a y equals x cubed graph. And so, again, this end behavior model of 2/3 x cubed is a pretty good graph, or a pretty good end behavior model to use, when you look at that graph. All right, finally this one, same idea. We are going to find our end behavior model, which we'll call g of x, by taking, again, the term of the highest power in the numerator over the term of the highest power in the denominator, and take a look what happens there. Your x's divide out. You could say g of x equal to 2/5, 0.4. That is the end behavior model for that crazy looking function. And since it's a constant, that tells you that this crazy looking function, for the most part, as you move out toward the infinities, is just a horizontal function. It just is modeled by a horizontal line. Okay. All right, finally, one last little example where I want to show you that for functions that are not polynomial or, a rational set of polynomials, you might have to do a little bit more investigation about the end behavior models. So in example 11, we're looking at the end behavior model for f of x equal to x plus e to the negative x. And what I did here was I showed this function graphed in a standard viewing window. Okay, I like to call it my little Nike swoosh graph. But then I showed the function graphed in the, sort of zoomed out viewing window. And what I want you to see here is that when we look at it zoomed out, especially to the left of x equals 0, the graph takes on certain properties that I would say look like exponential. And to the right of x equals 0, that graph definitely looks linear. And so what's happening here is based on the sign of the x values, when you have negative x coordinates, this term is taking over and the y values are very close to what the value of e to the negative x would be for those x coordinates. And for positive x coordinates, this actually has little effect as you move out toward higher and higher positive x coordinates, and so the function takes on values that are more like just the values of y equals x. And so what we would say here, okay, because we're just sort of seeing it graphically, that's enough for now to say that, let's call one of them g of x. G of x equals e to the negative x. That part of this function is going to give us our left end behavior model. And let's call it a different letter. H of x equal to x is going to give us our right end behavior model. Okay. And so sometimes that happens, and when we learn some better calculus, we can actually prove that these functions are a left and a right end behavior model, but that'll be after we learn something called L'Hopital's rule, which is super fun, but we're not going to learn it for a while. So right now we're just going to sort of mention that graphically that's what's happening. I encourage you to try this. You try where you're again looking at, there's a typo there, and behavior models for h of x equal to x plus sine of x. It's a pretty fun one, but I'm going to leave that one for you to try, and you can talk to me about it. We'll probably, if you're in my class, talk about it at some point, hopefully. And if you have any questions at all, feel free to reach out, let me know. And I hope this was helpful as usual. Bye.